Go.
Hi, we are the Wisconsin Autonomous Vehicle Engineering Society competing in this year's Promoting Electric Propulsion competition. I'm Chase.
And I'm Dylan.
And so starting off here, we have our power storage unit. And so with this power storage unit, we have two 96-volt lithium-ion batteries that were donated to us by the Engineering Research Center here on campus. And these batteries have 26 cells each, and each cell has around 3.4 to 3.6 volts in it. So also under here, we are working on our battery management system, as you can see. And this battery management system has a charge meter as well as a master controller unit that will show us the power output as well as give us the cell voltages of each individual cell and then each module. So also with this, we have our high voltage disconnect and our e-stop button. So if we hit it, it cuts all power to the motor. And then moving on to the bow of the boat, we have a 12-volt battery here encased that powers the trim, the battery management system, as well as our water pump for our liquid cooling unit.
Passing it off. I'm Trent.
I'm Nathan.
And we're going to talk a little bit about the controls. So in terms of steering, right now for the manned operation, this boat runs on a hydraulic steering system. For the unmanned competition, we want to pursue a long-term solution of a linear ball screw actuator that Mercury can provide us. But to try and get to the unmanned competition this year, we decided to go with a high torque servo and gears to drive through the steering wheel. As shown here, all we have is a servo that's mounted, and these gears will directly drive through the steering wheel. We did testing with the gear ratio to determine what torque we needed to withstand resistance from the water, while also giving us enough speed to turn somewhat efficiently when we're out on the water.
All right, so the next focus is the throttle control. And because the manned operation throttle goes through a motor controller, we had to get we had to be a little innovative with this solution. So basically with this throttle, when it's in neutral, it's a potentiometer that sends 6 volts back to the motor controller, and then that tells the motor controller that we want 0% throttle. When this sends out 12 volts, the motor controller sends out 100% throttle. So for us to be able to control that, we ran into an issue where our receiver from the controller only sends out like PWM signals at like really low voltages. So we found that our best bet was to, at least for this year's competition, make the throttle either on or off. And to do that, we're using this circuit where essentially we're using a low pass filter to turn the PWM signal into a analog DC source. That goes into an op amp that either triggers a high volt or low volt, and that will control a relay. And when the relay is closed and the switch is off, it'll only allow 6 volts to go back to the motor controller because we're going to hijack that signal line. And then when we turn the switch on, it'll open the relay, it'll add 4.5 more volts from these 3 AAAs, and that will reach 10.5 volts, which is about 70% throttle. As far as our e-stop that we need to implement, we did a lot of testing while doing our range testing. If we turn the controller off, it defaults all outputs to 0, which means the relay would be closed, we'd get 6 volts out, and the boat would be in neutral. And then, as well as our steering, all of those just cut out. And then, as soon as we want control again, we just turn the controller back on, it reconnects everything, and we can go from there.
So next, moving on to our propulsion system. This is a 25 horse outboard that was donated to us by Mercury Marine. And so in here we have a water-cooled brushless electric motor that we purchased from Thunderstruck, which is a local company. And so with this, we had to machine this motor mount that you see here, as well as a coupler to adapt our motor to the drive shaft of the outboard. So with this mount and the water coolant, our water coolant system, the outboard intake takes water and pumps it through our heat exchanger and then back out the boat. And so you can see here, we're still currently working on our setup with it, but we will have a inner coolant loop that is operated by a pump that connects to the 12-volt battery. And we will be using propylene glycol in this unit, which goes through our motor controller, motor, as well as underneath our batteries to cool the whole system. Also donated to us by Mercury Marine were 3 propellers. And so this fall we tested all 3 props and came up with this one is the most efficient and has the most efficient power output for our outboard.
Great. So now I want to talk about the collaboration our team has had with outside sponsors and faculty here at the University of Wisconsin. So we originally started as a team of 4 members until December when 4 new members joined the team to help work on the unmanned portion of the competition. In the fall, we established WAVES, which stands for the Wisconsin Autonomous Vehicle Engineering Society, as a student organization sponsored by the College of Engineering here on campus. Through WAVES, we have recruited 5 to 6 underclassmen members that are freshmen and sophomores that we are training and allowing to have hands-on work on the boat as well. Another sponsor we have that we meet weekly with is Mercury Marine. Mercury Marine generously donated our outboard and has been helping us with parts of our design throughout this whole process. We took a trip up to Fond du Lac, Wisconsin to Mercury Marine's headquarters and was able to see their manufacturing plant and the way they test their boats and meet with their autonomous team as well. In terms of different industries and how this compares to industry solutions, we've used Mercury's help and guidance to model our boat by their standards in a way, so we could have success when we go to the competition.
What's next? Here, we can talk about our steering solutions. So, for the unmanned portion, we had a lot of hurdles to get over. One of them was being the throttle, but another one was how we steer the actual boat. And we had to make a couple of modifications to our original design. The way that we ended up deciding on doing this is our large gear that actually drives the steering wheel, it presses into the current steering wheel using a system of keys, we'd say. There are a couple of ribs inside the steering wheel here that we essentially just push into the steering wheel. And the reason we had to do that is because this steering wheel would not come off the boat. And as such, we had to print our large gear in 2 parts and actually bring it together after the fact. So on the back here, there's this clamping mechanism that ensures that our gear will stay in one piece and operate as one piece during the competition. Additionally, we ran into issues on our pinion with making sure that it was set and that our servo didn't free spin when we were experiencing resistance. And the way that we ended up fixing this is initially we designed a set screw configuration, and ultimately what we ended up settling on was drilling a small hole through the servo shaft and actually putting a bolt through both the gear, or both the coupler and the servo shaft. This essentially gives us a better mode of connection to ensure that we won't slip. Additionally to this, there is a flat design on the servo shaft that we designed our coupler to use as well. Recently in testing, that's been wearing away, but we suspect once we print our final configuration of gears and we have a stronger material instead of something soft like PLA, that'll also help us ensure that the coupling is good and we don't slip when we're steering. I got to showcase the steering here a little bit. So as you can see from the controller, we're able to turn this, and that's gonna turn the piston back there. It operates in both directions. And our next step is going to be taking it out on the water and just seeing, how fast we can turn the boat while it's actually running. We're confident that this setup will be able to handle the resistance of the water, and that it'll last long enough for the competition. Like we said though, this is a short-term solution, and most of these ideas will most likely be scrapped in terms of a longer-term, more efficient solution in the future.
Also, something to note is this is just for testing purposes. We'll have an 18-volt battery hooked up, and that'll all be enclosed in the waterproof container as well. Throttle, yeah, we kind of touched on throttle, but essentially with this, we're just doing a lot of signal comparison and converting to be able to work with our current system, and then hopefully in the next year we can get things reprogrammed to make this a little bit more simple and be able to control it on our throttle stick.
Yeah, so just adding on to discuss some of the other things we've been working on throughout the year. So our steering console here has been reinforced and is very sturdy as compared to last semester. And we have also moved our power storage up about 10 inches. This will increase our, helping us get on the plane easier and just moving most of the weight in the boat more towards the helm. And then with our propylene glycol and our inner coolant loop, so we chose this substance due to its high heat transfer coefficient and as well as keeping and storing our boat outside. So we won't have to, since propylene glycol has a very low freezing point, we won't have to pump it out each time. But yes.
All right.
So thank you very much for watching. And again, we are the Wisconsin Autonomous Vehicle Engineering Society, and we're very excited to be competing this year.